Vítám nejenom vás, ale taky přednášející kolegyni Janu Strakovou. Přednáška bude anglicky. Já musím říct, že mi spadl kámen ze srdce, protože bych nevěděla, jak česky říct named entity. A přednášející mě uklidnila, protože říkala, že to je vlastně docela těžký a je to pojmenovaná entita. Takže budeme poslouchat přednášku o pojmenovaných entitách v rámci recognition pomocí neuronových sítí. Takže prosím.
Dear colleagues, it's very nice to see you all here again, coming back from maternity leave. So this talk actually has two motivations. One of the motivations is a practical rehearsal for my doctoral thesis defense, which hopefully is happening in June. And the second one is to show you my work, which you can also find in the doctoral thesis. It's already online as a draft. So the topic is neural network-based named entity recognition, also the name of my doctoral thesis. I am written here because I'm giving this lecture, but some of the work, or a lot of the work, is joint work with Milan Straka and Jan Hajic, my advisor. So what I'm going to talk about, maybe some first 30 minutes of the talk might be boring for you who know named entities, and especially for those who already heard some of my previous talks on this topic. And also, as it is supposed to be a rehearsal for the defense, I'm going to explain the basic and obvious things, but I hope to get to more interesting things towards the end of the talk. I'm going to present also our two papers, which form the basis of the thesis, and I would like to show what our future work might be in the next 1 or 2 years, and it's going to be more detailed than the future work section usually is in the talk, because we have plenty of ideas. So I would like to introduce them to you. Maybe you can comment on them. The source code can be downloaded either as name tag, which most of you know or use, and the related code can be found on GitHub. We hope to implement it in name tag soon, but writing the thesis took some time, so we hope this is going to be the nearest future work. So to get on the same page, I'm going to describe the task of named entity recognition very briefly. This is actually, these are real BBC headlines from September 2016 when I wrote this chapter in the thesis, and this is an actual print screen from name tag demonstration online. And you can see that a typical named entity recognition task is when the machine is given an unstructured, unlabeled, unannotated text. The machine is supposed to automatically identify proper names in the text, and these proper names are called named entities in this terminology. These usually are locations, people, organizations. So you can see name tag identifies some of them, and you can also find one mistake in the classification. The task of named entity recognition usually also includes the classification of the retrieved or discovered entities into a predefined set of classes: names, locations, and maybe here organizations. So this is actually a coordination, and it's supposed to be British and Irish Lions, but this is really difficult, and I just kept it there because I thought this was interesting mistake. Most of the training data for named entity recognition are newspapers, because this is how the corpora were created, by collecting newspapers. But obviously, or not obviously, but recently also, named entity recognition is trained on Twitter inputs, tweets. This is a little bit different task because they are very short. There is no context, and tweets usually do contain in them a higher density of named entities, because you tweet about something. That's why. Named entity recognition does not really have to involve only names and organizations, but any prominent or interesting chunks or sequences of text, such as drug names, parts of genomes, and so on. So there are also interesting shared tasks in molecular biology, where the tasks are to retrieve and classify parts of biological names in biological sequences. But I don't know much about this, so I'm just going to talk about a very typical setup for named entity recognition. So shortly on what a typical named entity recognition pipeline looks like. Typically, you get an unstructured text with no labels, but usually no part of speech text or lemmatization in it, and the machine applies what's not very surprising to you, a set of classification rules to the problem, and using some kind of supervised machine approach, such as maximum entropic classifier, or recently artificial neural network classifier, the machine outputs the solution to the task, which for named entity recognition looks like, for each token, the machine should say whether this token is outside of an entity or inside an entity. And it also should identify the beginnings, insides, and last tokens of an entity. This can be later decoded or optimized for the whole sequence, but let's not worry about it now. Our task is to find a good classifier which would model the named entities in sequences as tokens. So I am skipping ahead, but I'm just saying that this talk is going to be most of the time about neural networks that we use as classification as classification methods. So I believe I should introduce one or two slides about named entity recognition data, which is maybe many of you know them, but just quickly let's go through them. For supervised machine learning, manually annotated gold standard is obviously necessary. So for English, there are multiple such shared tasks or corpora or data with training, development, and test portion. For Czech, since 2007, there is Czech named entity corpus in its first version, and lately also in the second version, with corrected problems and issues. And other languages also have one or two corporas. Dutch, Spanish, German, and other languages. Some problems sometimes appear if you want to create or if you want to do multi-language named entity recognition. The problem is that there is no such, or I don't know about any such unification project that would unite named entity recognition corpora. If you know, let me know, or let Pavel Taufer know, because the plan is that something like universal dependency style named entity recognition data could be made from Wikipedia automatically, not only because we want a unified corpus, but also for all UD languages, but also to avoid licensing issues, because most of the named entity recognition data come with licensing restrictions. So we hope to release the data under some more free license. So if you have any ideas on this topic, let me know. Okay, about the data, about the standard and typical data. For English, the iconical or the most important referential corpus to show your reasons for is Cornell 2003 shared task in English. You can see the task is to identify and classify named entities into 4 classes only: person, locations, organizations, and others. The entities in the corpus are not nested. That means one entity cannot contain another entity, and one entity can only have one label. So you cannot say about one word that maybe it is a name of a club and also a name of a city. Czech named entity corpus, because I create Czech software for Czech, is a little bit smaller, and the hierarchy here is more fine-grained. The hierarchy was designed in 2007, and it has 2 levels included in each other. In the finer is included in the coarser one. So the coarse classes, there are 8 of them, and the fine classes, there is 46 of them. I'm talking about the revised hierarchy, which is in the second version of the corpus, and is a little bit changed from the first version. The corpus, since its beginning, may contain and does contain nested entities. That means one entity can contain another one, such as the city Ústí nad Labem contains the word Labe in it, so the word Labe is also annotated as such. And one token can be annotated with more than one named entity classification label. Okay, so you can see this task is a little bit more complicated. During the processing, one needs to take care of the nesting or embedding of entities, and also the absolute numbers of F measure of the results are a little bit lower in the absolute numbers. So having the data at hand, we need a set of classification features. A standard set of classification features is not really surprising to you. This is something that might apply to to most natural language processing tasks. Only the last two classification features are named entity specific. So for named entity recognition, rule-based orthographic rules are very important. That means that someone who understands the topic sits down and writes rules for the word capitalization. Maybe does the word contain special characters, how the time expressions look like in this language or in this corpora, and either they can be used as classification features or there can be regular expressions which act as binary features. So does this word match a certain regular expression describing, say, for example, time expression? So I'm again going to skip ahead and say that maybe in the future or towards the end of the talk, you would like to get rid of these manually designed features, because they need extensive feature engineering. So we are going to design a neural network which will automatically infer rules itself from the data, from the characters. Okay, this is an example of our current set of classification features that we use from Strakova from 2013, and it is part of NameTag. It did take some feature engineering, and it was one of the motivations why I started to learn about artificial neural networks because I wanted to avoid this for the next language we implement. Some other features, other than the local features, which are inferred from the current token and its surrounding, preceding, and following words, are non-local features. Non-local features, classification features, are such that the idea behind them is that if the word appears, maybe the name of the town appears several times in the text, in the discourse, it should always be labeled with the same label. So I am borrowing a terminology from Ratinov and Roth, 2009, and one approach is context aggregation. So instead of looking at classification, not instead, on top of looking at classification features of the current token, the classification features are taken as a whole from all its occurrences in the maybe larger window in the whole document. The other approach makes use of already performed classification in the past, and they call it extended prediction history. I did experiments with this in my preliminary experiments in 2013, and it's not on the slides, but I have to say it's a lot of work. The data gets larger. One needs larger models. The memory is larger, but the results were not so much better. So I stopped using non-local features for English. For Czech, it's another story, but we can get to that later. Wikipedia. Wikipedia is a big friend of named entity recognition and named entity people. Named entity people who deal with named entities love Wikipedia, and from time to time they always appear new and new papers in which the idea is boldly take Wikipedia as a large source of data which is partially annotated and full of named entities, and we can use it as our named entity recognition source. That's a great idea, actually, but as of yesterday, I haven't seen a freely available tool or freely available corpus, which would be for maybe just for academic community to download. So another motivation for Pavel Taufer's work is that he takes Wikipedia and creates a set of tools and a named entity recognition corpus automatically from Wikipedia, which would have reasonable licensing. And the tools would be available too. Like these guys created WikiNer, which should be what I'm explaining now, but I didn't find any code, and the project seems a little bit dead now. But if you know any of this, maybe you can tell me that someone has such a corpus or such tools, and they are available to everyone. So I will gladly be corrected here. Okay, so we are moving to the actual work. That's the inside of NameTag, and actually the alternative name of the paper should be how we learned to use the artificial neural networks, and we didn't know how to do it. So you will see how it went, and we'll slowly work our way up towards the current artificial neural network knowledge in named entity recognition. So in 2012, we sat down and wanted to create a new state-of-the-art named entity recognition system for Czech. What we had, artificial neural networks were getting more and more attention, but still were really not the machine learning method of first choice for named entity recognition, and we didn't find any very efficient, robust tools for named neural networks that could be embedded inside a small software solution, like not a big standalone not library framework, but we needed a small and fast tool. Torch appeared 2013 and TensorFlow very recently, so we wrote down our own classifier, neural network classifier. It was a very small tool which actually produced very nice results, and we were very happy about it. And now neural network classifier is actually inside of Morphodata, NameTag, and Parsito, and Parsito with some Parsito parses dependency trees, so there are some modifications, and UDPipe. So these were the first steps, and we did them for the named entity recognition. So what it had, it was actually very simple from today's view, as the deep networks are rolling in. But this is what we had in 2012, a very simple feed-forward artificial neural network, and a second one with hidden layers. And what we had was softmax output layer, which basically was a softmax normalization probability step at the end that creates probability distribution. We computed the parameters, or estimated the parameters with stochastic gradient descent, an online one, and we didn't know about mini batches yet. Someone told us, no, Martin Popel told us that we should use a regularization too, so we programmed that too. And we did a very big comparison of several use cases for named entity recognition, part-of-speech tagging, and semantic role labeling, the Connell 2009 shared task. And we compared stochastic gradient descent that we implemented, and we compared, at that time, very popular, Lample is a shortcut of the authors of the method, parameter estimation for maximum entropy classifier. Maximum entropy and a neural network that has a softmax output layer actually are equivalent models in the sense that they compute the same function. But for maximum entropy, these two methods, well, GIS was getting old, but Lample was very popular, and we found out that stochastic gradient descent is really it was not a really new finding, but we confirmed that stochastic gradient descent is very robust for large scale and sparse NLP tasks. We actually wrote a paper on our large use case comparison, but it got rejected twice, saying that the problem was that the reviewers didn't see the future in using artificial neural networks for large-scale NLP tasks. So we never published these results, but they are one chapter of the thesis. So this is where we were in 2013. We had a neural network classifier. We happily used it for named entity recognition, and we got nice results for Czech named entity recognition. This is for Czech named entity corpus of version 1.0, which was available in 2013. The numbers are F-measure, because for named entity recognition, per token accuracy is not a reasonable measure, since most of the entities in the corpus are not entities and are obviously retrieved as such or recognized as such. Then most of the recognizers easily get over 90-95% accuracy. So F-measure is a combination of recall and precision, a harmonic mean of them, and these are the results for Czech. Czech named entity corpus has two hierarchies: cores, eight classes, and then fine-grained 42 classes. And yes, I switched the columns, but you can see the numbers were good and we were happy, and we created name tag as a software solution for broad audience. English results, not so good. Why? I mean, not that bad, but also not best. The results fall well within the range of the participants of Connell 2003 share task. These are the winners of the share task. They were better than the current numbers on Stanford Parser, but worse than Suzuki and Isozaki and Ratinov and Roth. Suzuki and Isozaki use external Wikipedia data. Ratinov and Roth is the iconical, very important paper which since 2009 has had over, I don't know, 500 references. So this was a very important paper in 2009 which set up a new state of the art for a longer time, and it was actually overcome when artificial neural networks came to the scene. Yes, one of the criticism against this paper was that it was not actually very clear from the paper what the actual reason for its big success and skip against the other papers was. They tried many methods and then combined them together, and no one knew really if it was maybe the encoding or all the other methods they tried, but one way or the other, this was for a long time the state of the art for English. Okay, and the last paper and the last chapter of my thesis. In 2016, we already knew we want to use artificial neural networks. The neural networks have been through a very large advance in the last 3 years, and many things have appeared, such as training with dropout has been described and started to be widely used. Torch was available, TensorFlow was available, and word embeddings were available. So what we did, our motivation was to avoid labor-consuming feature engineering. So instead of having this large list, we wanted to move the burden from me or anybody else who needs to code the classification features, and maybe use a very simple set of classification features such as form, lemma, and part of speech if the morphological analysis is available, or maybe just infer the named entities from the form. So we are going to replace this simple artificial neural network with something more complex. So instead of having the complexity in place of the classification features, we are going to have the complexity inside the computational model. So this is the model of our artificial neural network, which we used in 2016, and it really is in place of the classifier. The network has two new advances in it in comparison to the previous network which we had. The first part is we use a completely different word form representation, and I'm going to talk about it more. I guess you are already assuming these are word embeddings and various kind of character level word embeddings. And also the training is different. I mean, it's still the stochastic gradient descent, but we have different activations and we have dropout during training. So softmax stays in the end because we still want probabilistic, we still want the network to output a probability of each word to be or not to be a named entity. So something is wrong? No, it's not. So a few words about word embeddings. Very probably boring for those of you who took the course on deep networks, but word embeddings. why they are useful for named entity recognition. Word embeddings as a mapping from discrete space as a natural language naturally is, because the words in the language occupy a discrete space, are useful because they map these tokens from discrete space to a continuous space of real valued vectors. And one thing is that the word embeddings, as they are currently understood and suggested by Mikolov and programmed by Mikolov in his Word2Vec program, naturally embed some kind of linguistic and semantic linguistic knowledge in them, and then they train them in unsupervised measure, in unsupervised way, without an explicit supervision of anyone from unlabeled data. So we have much larger unlabeled data at hand. Yeah, that's it. What it means in the context of named entity recognition, it means that if I see a word and I don't know it, and I have never seen it, and I have to decide is it a named entity or not, but it has a context, it appears in a context in which I have usually seen named entities, and I can, for some certainty, say that this is a named entity. Named entities can be either pre-trained on a large unlabeled corpus, and I'm using terminology from this paper, and then we will now call them pre-trained word embeddings, and then they act as a sort of a lexicon or a sort of hash table. So one can imagine that we have a large hash table. In one way, tokens come in, and in other way, real valued vectors come in, and that actually applies for the end-to-end fashion. So you can also train word embeddings specifically for the task of recognizing named entities. Soon it was clear that for some languages, especially for languages with more complex morphosyntactic structure, word embeddings are not enough, are too coarse, and maybe we want some other or more fine-grained means of capturing the inner structure of the word, like prefixes and suffixes. So in 2014, character-level word embeddings were suggested, and they improved part-of-speech tagging greatly. We can also look at them as offline pre-trained or learned for the task. So we have word embeddings that is on word level trained embeddings, and we have character level word embeddings. If you are familiar with word embeddings, I'm just adding specifically that we are using recurrent neural network word embeddings because they were known at the time, and so why and we used pre-trained word embeddings and learned for the task character level word embeddings. Why would we do that? I actually already gave a hint on this. We want to decide based on the context if the word is or isn't a named entity, and we want to infer specifically how named entities look like in this language or in this corpus. So the character level word embeddings are able to infer maybe that the time expression always contains a dot, or that the names of cities always contain a large capital in the beginning, and so on. So, and they need to be trained specifically for the task because we want them to capture the morphosyntactic structure of named entities with respect to the gold data. Look, something is wrong really. Oh, I'm giving away the results too soon. So our model, what we tried, we have the word embeddings, character level word embeddings, and the old good other methods like one-hot vector representation of part-of-speech text and words and lemmas and so on. we had, as a poor man's representation and also as comparison, we had character prefixes and suffixes of length 1 to 4, and we also later added also the old manual classification features. Now, a little bit about the character embeddings. This is the most technical slide, and when we go away, there is not going to be any more technical slides like this, but how it works. These are recurrent neural network character level word embeddings. So the word, say Prague, is split into characters. So the characters are on the input of the neural network, and the way we compute is that we feed the network with the word one character after another, and the recurrent neural network computes the output, and then we take the word, we reverse it, and we do the same backwards. So the characters go inside the recurrent neural network in the opposite direction. The way this is done is that people noticed very soon that the recurrent neural network tends to forget the information or the instances or the training instances that it has seen in the beginning of the training, and tends to remember more the information that it has seen towards the end of the training. So if we wanted to capture prefixes and suffixes, we go backwards and forwards. So we have two real-valued vectors. They get concatenated and go inside the larger neural network as another input together with the word embeddings and so on. I'm again going to skip forward and say that based on this observation, that character level word embeddings based on recurrent neural networks tend to remember prefixes or suffixes more, and also that for most natural language processing tasks, prefixes and suffixes are actually sufficient. People have come up with other models for character level embeddings, which actually concentrate or focus only on n-grams, beginning or ending n-grams. So I will get to these later. Actually, I talked about this. The second interesting part of the network is that we changed the activation of the internal neurons, that we use dropout, and then everything is pretty much the same, I think. Yes, I said everything. So, the results. Kolik máme ještě času? To je dobrý, to je super. Tak, děkuji. The results. So, this is the final number of 2013, where we used a very simple artificial neural network, which was equivalent to maximum entropy classifier, and we actually called it that way in the paper, maximum entropy classifier, but in the end it was actually programmed, or the parameter estimation was done in the artificial neural network way by stochastic gradient descent. Oh, I forgot to say, but maybe it's not important, that we use mini batches already here. So the results. This is with everything. We had gazetteers. We used two-step prediction. That means that the output from the first run of the algorithm is then fed to a second run of the algorithm as a classification feature, and it runs again. What else we had? Manual classification features. Basically everything, and it had lemmatization and part of speech text, and prefixes and suffixes, basically everything we could think of. And now we are at a situation where we have more complex neural network, and we program word embeddings and character level, recurrent neural network character level embeddings, and we only have forms in the input, so no other information. You can see that the numbers are not yet getting any closer to the state of the art that was at the time, but the network has much less information. Once we start combining the available data information, then it gets much better. So the interesting part here is a comparison between the third and the fourth line of the table, and these are manually taken prefixes and suffixes of length 1 to 4, and these are character level embeddings which are automatically inferred from the neural network, and you can see that the automatically inferred character level embeddings are much stronger, not to mention that the prefixes and suffixes are taken on a larger corpora without the respect to the task, while this is taken only from the named entity recognition corpus, which is a smaller one. If we combine both these approaches, then prefixes and suffixes don't add so much to the character level embeddings. And then the last section of the table, if we have also the morphologic analysis, in here we use morphodata for lemmatization and for tagging, we get much better results. The interesting part here is only with word embeddings trained offline and forms, lemmas and text, and no classification features, we already beat the simple artificial neural network with manual classification features. And the best numbers are combination of all. Interestingly, we don't even need the classification features to get nice results. Results for all corpora in available for Czech. This is basically just one corpora, but I am going to explain why there are 4 columns. We had Czech named entity corpus 1.0 and Czech named entity corpus 2.0. Sorry, I should not touch this, right? And this was very new in 2016, so nobody has yet published on it, any results on it. Then the Plzeň guys, Konkol and Konopík, created a version of Czech named entity corpus in which they flattened the nested entities into a non-nested, non-embedded version. They removed the ambiguities and they mapped all the annotation into 4 Connell classes: people, organizations, locations, and so on. So they created something like Connell corpus, and it's called extended Connell-like Czech named entity corpus. So that's why I am adding the results for this version of Czech entity corpus 2. English, again, not bad, but not best either. Why? This is very interesting. This paper, Lample 2016, I don't know how to spell it correctly, 2016, was actually published exactly the same month as our work. And there is one big, they have this very same neural network architecture as we propose. They also use character level recurrent neural network word embeddings and word embeddings. It's really the same, but there is a winning advantage to our network. And I'm going to explain, and it's our future work. Usually when one trains a classifier to classify and to classify a new natural language processing task, it is always useful if the classifier can optimize for the whole sentence. The pipeline, as it used to be usually used in named entity recognition, as we use it in our work, is such that it predicts for each token very separately its probability with respect of being or not being a named entity, and then takes these probabilities as an input for a dynamic programming or Viterbi or how you like to call it, and makes the optimization. Much better approach. We wanted to have it, but we didn't come up with it. We thought about it, but we couldn't come up with one. Would be to have the last layer of the neural network, the sentence level, and somehow include the sentence level optimization in the training of the network. But when we were submitting the paper, we didn't have this solution and didn't know how to do it, but these guys did, and the results are even better because they optimize and train for the whole sentences. So this is the winning advantage. Our future work. So I actually, during the talk, said revealed already a lot about our future work. So to sum up, this neural network architecture is actually not written in TensorFlow, because when I was writing it, TensorFlow was starting, so it's in Torch, but we would very much like to move to TensorFlow, so I need to implement it. And I already talked about named entity recognition corpus for UD languages, and I talked about I didn't talk about named entity linking. So a step aside, what's named entity linking? Currently, another approach to named entity recognition, is not another approach, is additional task to named entity recognition is that the named entity recognizer does not only have to recognize the named entity, but it should also disambiguate what kind of named entity it is, and it should preferably provide a link to some sort of knowledge base, Wikipedia, Wikidata, and so Wikipedia. So this is called named entity linking, and hopefully Pavel Taufer is going to do this. Also, you may know that we won a tender for. I'm talking about just my part here, but the tender is larger for deploying IT processing systems for text for Ministry of Interior, and NameTech is going to be a part of it in some way or the other. Other work, which is not about implementation and annotation, is the research. We hope to try more word embeddings, especially character level embeddings with convolutional neural networks, and very current work from last year with character level embeddings on an n-gram level. They are also called caragrams, and the other, I just forgot the other word, skip n-grams or so. So these three papers deal with very similar topics, and we hope to include these, and very much would like to improve our results more. You are very welcome to look at the doctoral thesis, to download the name tag. Maybe if you wait for more months, you will get the neural architecture and neural results in it implemented, and also the very current work is very recent work, can be found on GitHub. So that's all. That's the last slide. So questions or sorry. Okay. If you have questions or maybe suggestions for the project I just explained, then I would like to hear about them. Sorry.
I hope you can accept the questions both in Czech and yes, in English. So, as you wish. Prosím.
Někde, kde si ukazovala, že tam jsou na vstupu part of speech tagy a lemata jako one hot featurey. Dívali jste se, jak vypadají ty embeddingy potom těch part of speech tagů a lemat?
No, dívali, a já nevím, k čemu otázka směřuje, teda se přiznám, ale my jsme teda ty one hot representation třeba od forem jsme moc nepoužívali, protože jich je hodně a samozřejmě to zaplevelí jako ten vstup a začne to být velké a tak. Lemata jsme používali, ale hlavně tady jsme měli ty part of speech tagy, ne tak moc ty lemata, protože ty nám krásně pokryly ty word embeddingy. Já si to mám říkat anglicky, že jo? Mluví někdo tady jenom? Jo. Aha. Tady jsme měli většinou jenom ty part of speech tagy v té nejúspěšnější verzi, a tady jsme měli ty word embeddingy, ale lemata jsme tam už nepotřebovali dávat, protože to bylo jako zbytečně moc velké a stejně to pokryly ty word embeddingy. Ale byly součástí těch klasifikačních rysů, protože tam je všechno, jako Jako bychom neměli vůbec nic a já nevím, jestli odpovídá tu otázku.
No já jsem se pak dál chtěl zeptat, jestli ten prostor, kam se zobrazejí ty lemata, jak se má k tomu prostoru, kde jsou ty formy, když se to třeba nějak vizualizuje.
No, to jsme si teda vůbec nevizualizovali. No, my jsme jako vždycky my jsme dělali jakoby ten iterativní benchmarking, když jsme přidali nějakou featureu, když nám to, nebo nějaký model, optimalizovali jsme ho, co se týče parametrů i nějakých hyperparametrů, a když to bylo jakoby já jsem tady nedala všechny ty postupné výsledky do těch slajdů. A když nám to hodně pomáhalo, tak jsme byli rádi, nechali jsme to v tom modelu a když to bylo třeba zbytečně moc velké a nepřidalo to až tak moc velký přídavek, co se týče toho vyhodnocení F-measure, tak jsme to dali pryč. Protože často, jakoby my jsme nepotřebovali ten výsledek nejlepší za každou cenu, ale už jsme to dělali s tou vyhlídkou, že to pak půjde do name tagu. A nechtěli jsme tam mít zbytečně moc velké věci, které nepřidávají až tak moc. No. Ale žádný jakoby obrázky, třeba jak se to překrývá, jsme nedělali.
Děkuju. Ještě by mě zajímala jedna věc. Ten klasifikátor nakonec teda funguje tak, že je tam softmax pro každý z těch vstupních slov. A
ano.
Ty, co to teda optimalizovali přes celou tu větu, tam udělali nějaký conditional random field přes celou tu větu?
Já to musím ještě přečíst. Já jsem si to, jak jsme toho nakoukli, jako jsme, oni na to přišli, prostě jak jsme to chtěli udělat. Že tam mají tu větu na konci a mají to optimalizovaný, ale ještě jsme to jakoby nerozklíčovali, no, jak to přesně udělané. Protože jsme nad tím strávili docela dost času, bylo nám jasno, že to je důležité. Ale do doby, než jsme to odevzdávali na TSD, jsme to nestihli vymyslet. Takže budeme to muset od nich nějak obsat nebo se inspirovat. No.
Děkuju.
Děkuju. Já bych se chtěl zeptat, mě tam není jasná jedna věc úplně na konci.
Kam mám jet?
Pokud to chápu správně, tak teda pro jednotlivý tokeny dáš nějaký predikce a říkáš, že žádnou globální optimalizaci neděláš, ale jestli je to postavený na tom bylaw schématu, tak pak tam můžou vzniknout nějaký nekonzistence asi, že jo?
No jasně, ta dynamika na to musí být upravená.
Ale i bez když to bude úplně bez té dynamiky, tak tam musí být nějaký jako postproces, který to trošku...
No, to je pravda. I kdyby to je takhle, můžeš si vzít ty výsledky toho, co je nejpravděpodobnější výsledek na tom tokenu a říct, jakoby tenhle token je to, co tam vyšlo nejpravděpodobnější a už nedělat vůbec žádnou. A pak by to bylo nekonzistentní, no, když neuděláš žádný postprocessing na to, že nesmí být vedle sebe, tohle to je poslední slovo a tohle to je zase poslední slovo.
Přesně
to
tak,
nejde, že?
Je to třeba trošku podobný parsingu, kde já můžu vracet nějaký grafy, které nejsou stromy, budu mít lepší UAS, ale nejsou to stromy, že? Tak.
No, ale to by ti nikdo jako, za to bys nedostal vůbec vynadáno v té F-measure. Tam prostě jde o to, jestli si jako, nenašel bys tu entitu, že jo? A jakoby dostal bys si penalizaci nejenom za to, že si zbytečně řekl, že to je last of an entity a určitě ani jeden z nich nemůže být. A ještě by si dostal penalizaci za to, že jsi nenašel tu, co tam měla být. No, jako v tomhletom směru ano. Ale jenom jako v malém bodíčku. No, kousíčku ty F-measure. Ale ta globalizace výsledná není důležitá jenom proto, aby se zvedlo to F-measure, což se teda zvedne. Ale i proto, aby tam nevznikaly nesmysly. No.
Děkuju.
Jo.
Já jsem se chtěl vrátit naopak někam úplně na začátek té premise, že je jenom jeden význam v jednom diskursu pro každou tu named entity. Tak se chci zeptat, jestli tahle ta premisa se nemůže stát nebezpečnou a jestli ještě držíte, možná je to tam citovaný z nějakých počátků zpracování, protože vezměme si třeba Paříž, pokud míní francouzskou vládu nebo něco takového, můžeme si být jistí, že v té samé knížce, v těch samých novinách se neobjeví ve významu francouzské hlavní město. Třeba, já nevím, Paříž je proti imigraci, tak já se do Paříže hned tak nepodívám. Hříčky tohoto druhu jsou pro mnohé texty konstitutivní, třeba korespondence Voskovec-Verik, jo. A tak teda bych chtěl položit takový úplně prostý minimální otázky, jestli vůbec nějak zacházíte s vícevýznamovými named entities, jestli registruje nebo máte nástroj, jak uchopovat významy, které nenajdete v žádné Wikipedii. Jako třeba Paříž ve významu konkrétního fotbalového týmu, že Paříž hrála s Lyonem tak a tak. Jo? To nikde se ve slovníkách nenajde. nebo 10 deka Paříže, jo, pařížský salát. Je pravda, že vlastně touhle premisou, která zasahuje do semantiky, si kolem těch named entities přiděláváme starosti, jaké u běžných slov vůbec nejsou. Je úplně jedno, v jakém významu je použito oko, prostě lema je oko.
Tak to děkuji, to je zajímavá otázka a já ji odpovím postupně, tyhle ty otázky. První věc k tomu, jestli ještě stále držíme one sense per discourse, tak nedržíme, protože to zavedli to, nebo já nevím, jestli to zavedli, ale hezké výsledky s tím měli tihleti autoři. Mně se to líbilo, chtěla jsem to taky naprogramovat, tak jsem to jako zkusila a ukázalo se, že nejenom, že to je velice pracné a musím si držet v ruce celý ten korpus a tak a zvětšují se mi ty modely, ale nedalo mi to žádné lepší výsledky, ještě se to začalo trošičku rozbíjet a celkově bylo složitější udržet to celé, jakoby ten model v pořádku a tak, takže jsem to rychle opustila. Není to dokonce, tady tyhle, já jsem to řekla jenom pro pořádek, že to někdo používá, že to je zajímavé, že by se to mohlo líbit někomu, kdo rozumí diskurs tady a tak, ale já to v těch modelech nemám ani v jednom. Takže to je první věc. A druhá věc, to, co jste říkal o tom, že by se mělo odlišit Paříž jako salám a Paříž jako, tak to hodně záleží na tom, když si sedne ta skupinka těch anotátorů nebo na zadání té úlohy. Někdy za vámi přijde někdo a řekne, my bychom chtěli, abyste nám rozeznávali Paříž jako salám a Paříž jako město a jako fotbalový klub. A tady máte data, ve kterých je to vyznačené. Tak ten stroj ty data dostane a naučí se, že se to slovo salám Paříž vždycky nachází v blízkosti toho slova salám a příště ho znovu označí jako salám. Ale stejně tak jakoby fotbalový klub Paříž, pokud je to v těch datech označeno, tak se to taky naučí z toho kontextu. Ale jindy zase přijde třeba zadání, my to nechceme rozeznávat, tak chceme rozeznávat prostě jenom města. A tam by se mohlo stát, pokud jakoby je ta klasifikace nebo hierarchie těch entit jenom čtyř jako osoby a místa a organizace, tak tam skutečně by spadlo všechny tyhle výskyty do té jedné škatulky město, protože převládající výskyt toho slova Paříž je město. Takže třeba ten Connell soubor, ten Connell data, ten Čertář má jenom 4 třídy a tam se to bude dít. V češtině ten Czech Named Entity Corpus má v současné době 62 velmi detailních tříd a tam by se to začalo asi rozlišovat.
Poděkovat za přednášku a hlavně za to, že jste si řekla, že představíte svou doktorskou dizertaci před větším publikem dřív, než budete přednášet před komisí a to myslím, že by mělo být pravidlem a ne výjimkou, ale nicméně velmi to hodnotím, že jste to tak právě udělala. Takže ještě jednou děkuji moc krát i za tohle, nejenom za tu přednášku. Děkuji vám za účast a příští týden, jestli se nemýlím, Martin bude taky z našeho okruhu referovat o svém.
O Universal Dependencies a Framework of Daty.
Výborně. Takže děkuji moc krát a těšíme se. Naschledanou.